After discussion of the closed loop analysis, after discussion of the various problems based on the controllers, the closed loop analysis as well as offset, please note that in control section, offset calculation and block diagram reduction is very important. The block diagram reduction is important because then only you'll be able to do the offset calculation. And yes, I think I have discussed in previous lectures also that please keep a note that for a particular topic, which transfer function I am using, whether I am using closed loop transfer function or open loop transfer function. If you remember, for offset calculation, we use the closed loop transfer function. But which closed loop? If you were giving a step change in set point, then we were using the servo closed loop transfer function. If you were giving a step change in disturbance, then we were using regulatory closed loop transfer function, but it was always a closed loop transfer function. Now, a very important section of process control, offset के बाद जो अगला important section है वो stability analysis. But again, I am telling you, for checking whether a system is stable or not, a control system after applying the controller is stable or not, we have to again understand the block diagram reduction. However, I have discussed कि आपके पास जो block diagrams आएंगे वो standard negative feedback control loop होंगे. And for negative feedback control loop, I gave you that it is the product of the forward path blocks divided by 1 plus open loop transfer function. Whenever I am discussing a concept, please be careful whether I am using closed loop transfer function or open loop transfer function. Let us write the definitions now. We will now discuss about stability. This stability analysis is completely a different section, and 100% there will be 1 or 2 problems from this entire stability analysis. Okay, so let us write the definition. First definition, first point. From steady state operational condition. From steady state operational condition. From steady state operational condition, if a system is disturbed by, what is the meaning of from steady state operational condition? Means the system was earlier operating at steady state. Okay, if a system is disturbed by a finite or bounded input. I hope you remember what is the meaning of bounded input. मैंने आपको पहले ही बताया था when I was discussing inputs that you can always check whether a function, mathematical function, is bounded or unbounded. So we discussed that which inputs were bounded and which inputs were unbounded. So from steady state operational condition, if a system, please be careful here because I told you that कि ultimately in process control definitely there will be a question, and from stability and from stability analysis 100% there will be one question. It can be from Raut, can be from Bode, can be from frequency response, but stability से एक question या 2 question भी आना must है, ठीक है? So please be very careful here in all the definitions. If a system is disturbed by a finite or bounded input. Now please recall that how we were calculating or how we were checking whether a function was bounded or not. Okay. So by a finite or bounded input. So from steady state operational condition, if a system is disturbed by a finite or bounded input and the resulting response is also finite or bounded, then the system is said to be stable. Then the system is said to be stable. You can change the paragraph after this and you can write after this. If under the same circumstances, if the resulting response is unbounded or infinite, if the resulting response is unbounded or infinite, infinite, then the system is unstable. Then the system is unstable. Fine. Note down this. This is the definition of stability of a system and or instability of a system. What is the definition? Now, we will write a number of conclusions from this definition. First of all, if a system is disturbed by a bounded input, bounded can also be written as finite. If a system is disturbed by a bounded input, do you remember the examples of bounded input? Step input was bounded, yes. Sinusoidal was bounded, yes. Pulse, impulse was bounded, yes. Ramp was unbounded. Okay, so if a system is disturbed by a bounded input and even the output was bounded, if the output means response, even if the response is bounded, then we say that the system is stable. Otherwise, under the same circumstances, what is the meaning of same circumstances? Same circumstances means input is bounded. If the input is bounded, but the response is unbounded or infinite, okay, in that case, the system is unstable. One conclusion from this discussion is we always check the stability of the system. We always check the stability of the system. लिख लो. We always check the stability of the system. Stability of the system by using bounded input. System with the help of bounded inputs. So we will never give unbounded input. See, input must be bounded. Now output is bounded or unbounded. It will decide whether the system is stable if the output is bounded or unstable if the output is unbounded. But input should never be unbounded. So we will never give ramp input for checking the stability of the system. So we always check the stability of the system with the help of which input? Bounded input. Fine, with the help of bounded input. Okay? So remember this point, whenever we are going to check the stability of a system, the input given to the system must be bounded. After that only you are going to check the response. So we also use a word which is called stable system. Means stable systems are those systems which can be written as BIBO, BIBO system. What is the meaning of BIBO? BIBO means bounded input, bounded output. Those systems which provide bounded input, which provide bounded output, when they are disturbed by a bounded input, are called stable systems. Now, this is the definition of stability. अगर आपसे कोई पूछे how you define a stable system, this is the definition. Don't try to tell them the Routh criteria. Routh criteria is a test. That is not the definition of stability. Stability definition is this. The input is bounded and the output is bounded, so the system is stable. Can I say that by using this concept, can I say that, just think about this statement. A first order system is always stable. Think about it. A first order system is always stable. Can I say like this? Chalega? Yes or no? A first order system is always stable. Why? You saw that whenever I was giving, think about the first or second chapters when I was discussing the response of a first order system to step input, which was bounded. What was the response? The exponentially rising response. Okay, which was also bounded. We checked. मैंने सारे output भी check करवाए थे कि even output is bounded. You saw that for a first order system, whenever you gave bounded input, the output was always bounded. So can I say that a first order system is always stable? According to this definition, yes or no? According to this definition, yes. Right? But can I say that a purely capacitive system, do you remember what was purely capacitive system? The example where we used a pump at the outlet of the tank. A purely capacitive system is unstable. Can I say this? Yes or no? What can you say about this statement? You saw that when there was a purely capacitive system and I gave a step input, what was the response? Try to recall. Panne palat ke mat dekhna, hai na? Turn the pages of your memory and try to recall that when we gave a finite input, to purely capacitive system, it was a ramp response, because it was a kind of purely integrated. It integrated whatever input you give. So if you are giving a step input, it integrated to give you ramp input, and therefore a purely capacitive system is unstable. Don't think sir bas yahi dono type ke system hote hain. There are a numerous kind of system where you can check the stability of the system, but I gave you one definition. Till now, I have just given you one definition, that this is the definition of stability. Based on that, whatever I know right now, whatever I can recall from the previous lectures, I can say that a first order system is always stable, a purely capacitive system is unstable. Because I know that when I gave bounded input, they gave me, this one give me unbounded output. Okay, right. So these were some conclusions. Next definition. So please remember that for checking the stability, we never use unbounded input. We always use bounded input and then check the response. Now write the next point. If a process without any control means there is no controller. Okay. If a process without any control means there is no P controller, PI controller or whatever. Okay, if a process without any control system is studied to reveal its dynamics, studied means we are observing such a system to reveal its dynamics. We are studying the system to find how it is going to behave, means the dynamics. But the system is not having any control. Okay. Now, the result of this study, if a process without any control is studied to reveal its dynamics, then the result is commented as, अगर इसका कुछ result आएगा, then you are going to use this line, these words as open loop stable, if it is stable, or open loop unstable, right? If you are not having any controller, or suppose if controller is there but the loop is cut, the closed loop, the feedback path is cut. In that case, if you are checking the stability of the system, then you'll comment your result as open loop stable or open loop unstable. Okay. Now, when a process together with its control system is studied, when a process together with its control system, when a process together with its control system is studied, when a process together with its control system is studied to reveal its dynamics, then the result is commented as to reveal its dynamics. Then the result is commented as, I will use the following words, commented as closed loop stable or unstable, as closed loop stable or unstable, or closed loop unstable. Okay? This is some basic definitions in stability. We must know these things, right? So note down these things. Okay. And now we will talk about how to find stability, but how to check the stability of a system. But before going to that, let us talk about the transfer functions again. You know that this was the second point. Let us write the third point. You know that, see, any transfer function, suppose we are talking about the closed loop transfer function, we will use the closed loop transfer function for checking the stability. I told you to be very careful when I say this, that I am going to use closed loop transfer function for checking the stability. Okay. Open loop can also be used. In that case, the system will be commented as open loop stable or open loop unstable. Suppose there is a closed loop transfer function. How you denote the closed loop transfer function? it can be servo closed loop or regulatory closed loop, it is always a function of S in the numerator divided by denominator. Denominator is also a function of S. You have studied in your high school algebra that the roots of numerator are called zeros and the roots of denominator are called poles. So here, if numerator is equated to 0, suppose it is, you can break it into linear factors, you equate it to 0, you will be getting some roots of the numerator only. Let us term them as Z1, Z2, Z3, etc. Right? These are called zeros of transfer function. Don't say zero of numerator. These are the roots of numerator. Write down Z1, Z2, Z3. Z1, Z2, Z3 are the roots of numerator, right? Are the roots of numerator, and they are called zeros of transfer function, and they are called zeros of transfer function. Which transfer function? This transfer function. So when you equate the numerator of a closed loop transfer function equal to 0, they are called zeros of the closed loop transfer function. Similarly, you can also equate denominator to 0. Let me write here only. Let us make the efficient use of this space. So, okay. If, I'm writing here, if denominator, which is a function of S, is equated to 0, you will be getting some values of S. Let us call them P1, P2, P3, etc. Now, P1, P2, P3 are the roots of the denominator. P1, P2, P3 are the roots of the denominator, and they are called poles of the transfer function. Okay? And they are called poles of the transfer function. So first of all, it should be clear that what is the meaning of zeros and what is the meaning of poles. ठीक है, पहले इतना लिख लो. ठीक है, pause करके वीडियो लिख लेना, आगे बढ़ते हैं. Okay. So first of all, you must know that what are zero, what are poles. Okay, I mean I can always write this closed loop transfer function as, इसको यहाँ भी लिख लो. देखो, closed loop transfer function can always be written as the zeros. So I'll write S minus Z1, S minus Z2. I hope this is visible. है ना? S minus Z3 dot dot dot, and S minus P1, S minus P2, S minus P3 dot dot dot, like that. I can always write a transfer function like this. So the roots of the numerator are called zeros and the roots of the denominator are called poles. देखो कभी जब आप, it is also important to understand what are the words you are using. Suppose you are using the word roots, then don't say that the roots of transfer function. There is no meaning of roots of transfer function. Roots are always for some equation, and equation is either the numerator or the denominator. So you should say roots of numerator, roots of denominator. Now the roots of numerator are called zeros, roots of denominator are called poles. Fine. Okay. So note it down everything. This is going to be a very important discussion regarding this process control part. The most important is stability analysis only, right? And most of the question you will also find from this stability analysis section. Okay. Right. So, okay, P1, P2, P3 and all, fine. Okay. So you have noted it down, right? Now the next conclusion is very, very important, that stability of a system only depends upon its poles and not zeros. System means the closed loop transfer function, which represents, what is closed loop transfer function? Closed loop transfer function represents the entire controlled system. Okay. So the stability of a system only depends on the poles Now when I say poles, don't say poles of denominator. Poles are for transfer function. So poles and zeros are used for transfer function. Roots are used for numerator and denominator. Only depends on the poles of closed loop transfer function and not on zeros of closed loop transfer function. Important to understand. The zeros only have some role in the nature of response. They can of course change the nature. I think we have discussed the numerator dynamics, that how the numerator dynamics affect the nature of the response. Suppose if a system is unstable, it is not like that a numerator is present and it is going to make the system stable. No. If a system is unstable, the numerator won't make it stable. Or if a system is stable, the numerator won't make it unstable. So numerator has no role in deciding the stability. This you must understand. न्यूमरेटर का कोई काम नहीं है, वो स्टेबिलिटी डिसाइड नहीं करेगा. कौन करेगा? डिनोमिनेटर. ऑलवेज poles are important for checking the stability. And yes, I just one point came into my mind. Many students ask me that, sir, is root locus is in the syllabus of process control or Nyquist plot? So please note that root locus is not there. Most of you, I know that you know these things, but those who are studying in pre-final year or they are preparing for the first time, they have this, because we discuss root locus in a lot of detail in semesters, and even the Nyquist plots. The root locus and the Nyquist plot are not in our syllabus. तो ऐसा नहीं है कि आपने कहीं पे XYZ टेस्ट सीरीज ज्वाइन कर ली and they are giving you questions for root locus, because I know who frames those questions. The students, the PhD students or the teachers of electronics or electrical, they are going to frame the control question, and nobody gives a second thought कि मैं इन बच्चों को क्या दे रहा हूँ. They will provide you those questions based on root locus, sometimes based on Nyquist plot also. I have seen the question in test series of various organizations. They give you questions on Nyquist plot. तो जो सिलेबस में है ही नहीं, then ultimately you lose your confidence कि नहीं ये सर ने नहीं पढ़ा है, ये नहीं आता. You won't find a single question on Nyquist plot in last 30 years. And it is also written, it's not written that it's not there in your syllabus, it is written there. Okay, so don't go through the discussions of root locus or Nyquist plot. Okay, so only poles are responsible for deciding the stability of the system, but not the zeros. Okay, what else? Okay, suppose I'm just taking an example. Let there is a second order system. Do you remember the differential equation of second order system? Yes, differential equation of second order system. याद करो, कॉपी खोल के नहीं देखना है, अभी देखो, अभी लिखो. This is the way you revise. When you are reading a subject, the moment something you want to recall, never turn the pages of your notebooks. Again, I'm saying turn the pages of your memory and try to recall. Can you write without looking anywhere what is the standard second order differential standard differential equation for a second order system? If you remember that it was, I'm writing this in the form of a deviation variable. So it was tau p square d square y by dt square plus 2 zeta tau p dy by dt, okay, plus y, I think this was the equation, okay, is equal to x, right, plus y is equal to x. Okay, sorry for this. So I hope you remember this equation, okay, that plus y is equal to x, where y and x both are a function of time. Suppose I'm considering this differential equation. Now all of you must have studied the methods in your semesters as well. और नहीं भी पढ़ा है तो ये कोई difficult चीज़ें नहीं है. We have studied this in high school also, that how to solve a high order differential equation. You are going to make first auxiliary equation. And what is the auxiliary equation for this? Do you remember how to write the auxiliary equation? You'll write this as d square, okay, d square or tau p square d square plus twice zeta tau p into d plus 1, that multiplied by y is equal to, I can write this equation where d is the differential operator. And what is the auxiliary equation? Auxiliary equation will be this step. D square tau p square plus twice of zeta tau p into d plus 1 is equal to 0. This is the auxiliary equation. And then you know that the nature of, or let's write the solution of the differential equation. This is very basic concept. The solution of the differential equation, do you know what is the meaning of solution of a differential equation? Solution of differential equation means capital YT. The solution of differential equation means capital YT depends upon the nature of roots, upon the, ये पहले भी बातें शायद एक बार मैं कर चुका हूं, upon the nature of roots of auxiliary equation. Correct? So what are the roots of this auxiliary equation? Whether they are real and unequal, whether they are real and equal, whether they are imaginary conjugates. Okay. So depending upon that, you'll be having your solution, and solution को और कुछ नहीं बोलेंगे. What is solution? Solution is nothing but the response. Now let us do one thing. Let us take Laplace of this equation. Laplace of above dE. Can you take Laplace? Many students say, sir, we must read or study the topics of Laplace or differential equation before process control. Is it so? I'm not using, not even, these are the, except this Laplace, these are the definitions which we have studied in class 12th. So, yes, it is all about your mentality. Sometimes we make a mentality that without studying the differential equation, we will not be able to understand this. Once this mentality is created, then doesn't matter however hard you work, you will always have a doubt in your mind कि ये मुझे समझ नहीं आएगा, है ना? So don't let these kind of thoughts come into your mind. Don't let these kind of thoughts dominate your mind, because there's nothing, this is not a very difficult or very complex kind of mathematics. Or if you don't know, then learn here. At least whatever I'm saying, at least learn that much. And don't worry about the future. है ना? Work in the present. Future will be automatically set according to your targets, according to your requirements. ठीक है? But if you're worrying about the future and you're not working in the present time, then बस worry करते रह जाओगे and होगा कुछ नहीं, है ना? So you have to work here. So Laplace of above differential equation. What is the Laplace? Tau p square s square y bar s. Now what is the Laplace of double derivative s square y bar s plus twice of zeta tau p s y s. Okay. Y bar, you can place a bar here because we are using this notation, plus y bar s is equal to x bar s. Am I right? This is how we take Laplace. Now do one thing, that write the transfer function. What is the transfer function? Y bar s by x bar s. Look, Laplace and differential, they are related. They are the same thing, but they are only present in opposite parallel worlds, kind of parallel worlds. Okay. So Laplace, S domain and T domain, I told you in the very starting that they are kind of parallel worlds. Okay. So this is the equation. Now can you write the transfer function from here, which says that y bar s by x bar s is equal to, I think numerator will be, okay, here it was Kp for second order system. Kp is 1, assume, no problem. Is equal to, because numerator is not going to decide the stability. So numerator aap Kp लो या नहीं लो, doesn't matter. It will be tau p square s square plus twice of zeta tau p s plus 1. Okay. Now if I ask you ki what is the denominator here, you will say that, sir, the denominator is tau p square s square plus 2 zeta tau p s plus 1. Now, can you tell me what is the pole of the transfer function? Poles of the transfer function means roots of tau p square s square plus twice of zeta tau p s plus 1. And now see this equation. Roots of auxiliary equation means roots of tau p square d square plus twice of zeta tau p d plus 1. Now what do you think? Are they the same equations? Only s and d they have interchanged. They are the same equations. Means the poles of the transfer function and the roots of the auxiliary equation from which this transfer function is obtained are same. So either I say roots of auxiliary equation or I say poles of transfer function, they are exactly same thing. मतलब जो poles आएंगे ना किसी transfer function के, poles उस transfer function के they are identical. भाई ये transfer function आपने किसी differential equation से बनाई थी. Where this differential equation? This. Now if you find the what is the purpose? What is the purpose? The only purpose is this. We are doing everything to find this yt. This is your purpose. Now you find yt by taking the Laplace inverse, or you find yt by solving the differential equation. It is exactly same. You find yt by taking Laplace inverse, or you find yt by solving the differential equation. It is exactly same. Fine. So whatever method you use for finding the value of yt, that doesn't matter. Okay, whether you go for Laplace or you go for differential. But in differential, when you are going to find yt, you will find the roots of auxiliary equation, and then we have various methods. And in Laplace, if you want to find yt, we will check that, or if you want to check the stability, we will find the poles of transfer function. Please note that poles of transfer function and the roots of auxiliary equation, they are identical. Fine. Okay, means what we have concluded now, that the poles of transfer function are identical to the roots of auxiliary equation. Which auxiliary equation? Roots of auxiliary equation of the differential equation from which the transfer function is obtained. Root of auxiliary equation of the differential equation from which the transfer function is obtained. So poles of closed loop transfer function is equal to roots of auxiliary equation of the differential equation from which the transfer function is obtained. ठीक है? तो ये जो ट्रांसफर फंक्शन है ये डिफरेंशियल इक्वेशन का ही दूसरा रूप है ना? So transfer, whether you talk in terms of S domain, then you have transfer function. If you are talking in terms of time domain, then you have differential equation. Okay. So roots of auxiliary equation, okay, poles of closed loop transfer function are same as the roots of auxiliary equation of the differential equation from which the transfer function is obtained. So this likh lo. This is one more conclusion. We will use this conclusion to check a system is stable in which conditions. We know that based on the roots of auxiliary equation, the yt response, this is, what is this? What is response? This is the response, and we want to check whether the system is stable or not. So how to check? This is the response. If this yt is bounded, then your response is stable. And please note one thing, if I'm saying roots of auxiliary equation of the differential equation, it means poles of the transfer function. Correct? You know that based on the roots of auxiliary equation, we have various nature of responses. Let us make some categories. Let us see that how or what are the roots of auxiliary equation in those cases, what is the nature of response, and let us check whether the response is stable or unstable. Fine. So yeah, this one. Okay. So yt, fine. So do you remember that what is the nature of auxiliary equation, and based on that, what are the various kinds of roots? If yes, then okay. If not, then try to recall a little bit, revise a little bit here only. और जब आप पढ़ेंगे तब इसको डिटेल में पढ़ लेना, not a problem. But यहाँ पे जितनी जरूरत है वो देखो, I'm writing here roots of auxiliary equation of the differential equation. Clear? Or poles of transfer function of the differential equation. Actually, we should not write transfer function of the differential equation. We should write transfer function of the system. But you know that differential equation is something which represents the system. Okay. What are the possible cases? It is possible that the roots of the auxiliary equation of the differential equation is real and different. Let's see what happens in that case and what is the solution in that case. We have to check that whether the response is coming that is bound. देखो अभी तक आप stability की क्या definition जानते हो? We only know so far that if the response is bounded, then the system is stable. If the response is unbounded, then the system is unstable. तो अभी तक बस इतना ही पता है. But इससे question solve होगा क्या? No. Question solve करने के लिए we have to make some mathematical rules for checking the stability of the system. Let us do that. Suppose first case 1, that roots are, now please note I am writing roots, but you have to understand roots of auxiliary equation or poles of transfer function. Roots are real and different. Suppose we have two roots. There can be more than two also. What are the roots? Real and different. Suppose they are m1 and m2. Do you remember what is the solution in this case? Try to recall. If the roots are real and different, then the solution is yt is equal to c1 into e raised to the power m1t plus c2 into, where c1, c2 are arbitrary constant, e raised to power m2t. Okay? This is the response. Now we have to find whether the response is unbounded. How to find response is unbounded or bounded? Whenever you want to check whether the response of a system is bounded or unbounded, in that case, you put t tending to infinity, right? Let us do that. But let us take various cases here. Case 1 is this, but what the roots are real and different, right? बस मैंने कहा कि real and different, but they can be positive, negative, उसकी तो बात करें. Let us make more cases. Suppose if m1 and m2 both are positive, both are positive, then you'll see that the value of yt at t tending to infinity. What is the answer? Tell me. m1 is positive, t tending to infinity, so e raised to the power m1t tends to infinity, e raised to the power mt2 tends to infinity. You can say that, होगा ना? If roots both are positive, in that case, as time grows, e raised to the power m1t also grows exponentially and becomes infinity. So yt at t tends to infinity becomes infinite. Sorry, infinite. What is the meaning of infinite? Infinite means unbounded. What is the meaning of unbounded? Unbounded means unstable. Fine. What does it suggest? It suggests that if the roots of the auxiliary equation or the poles of the transfer function are real, different, positive, the system is unstable. This is how we have to find, we have to check whether what are various cases, and then we are going to make some rules. Okay, let's do one more thing. Suppose m1 and m2 both are negative. What you are going to that in that case? Suppose m1 and m2 are negative. In that case, it will be, the equation remains same, only this m1, m2 will become negative in that case. So what is yt at t tending to infinity? Suppose m1 and m2 are negative. So as t tends to infinity, e raised to the power m1t becomes 0. So this is 0 plus 0. Fine. And this is 0. And I told you initially that 0 is finite. Finite means bounded. Bounded means stable. Sorry, not unstable, it is stable. Fine. One more case. देखो बस भाई मुझे यही चेक करना है कि response, it must be bounded. That is the definition of stability of a system. And how to check whether the response is bounded or not? Put t is equal to infinity, or you can use the final value theorem, but we are right now talking in time domain. So I'm putting t tending to infinity. Similarly, suppose we have one more case. m1 is negative, but m2 is 0, or vice versa. m1 is 0, m2 is negative. In that case, the equation remains same, but your yt will become, see, m1 is negative, right? So what is yt? Yt will be c1 e raised to the power m1t, where m1 is negative. You know that m1 is negative, so I'm not writing minus m1. But this m2 is 0, so e raised to the power 0 is 1 plus c2. What do you think? So yt at t tending to infinity. This remains c2 and this becomes 0. So the answer is, because m1 is negative, so this becomes 0 plus c2. Answer is c2, which is finite, which is bounded, okay, and bounded means stable. See, many cases I have discussed here. What is your conclusion right now? If the poles are, so far, what is the conclusion? If the poles are negative, then the system was stable. If one of the pole is negative, other is 0, then also the system is coming out to be bounded, so stable. Fine. This is how you check whether the system is stable or not. Okay, and this is how I will make rules. Suppose if I just make one definition of, that was a definition, BIBO. But how you are going to apply on the numerical problem, that is why we are doing this, and we are trying to make conclusion. Case 2. What is the other possible nature of roots? Roots are real and equal. Roots are real and equal. Fine. So in this case, you know that the roots are m1 equal to m equal to m. m1 equal to m2 equal to m. Do you remember what is the solution for this case? I think it was c1 plus c2t into e raised to the power mt. This used to be the solution when we have repeated roots. Suppose if there were 3 roots, then c1 plus c2t plus c3t square into e raised to the power mt, if all of them are identical. ये differential equations के बहुत basics है. अगर आप बोलोगे कि सर आप बिना differential equation पढ़ाए ये क्यों पढ़ा रहे हो, तो ये पढ़ाने वाली चीज़ें नहीं है. अगर आप बस ये आप थोड़ा सा भूल गए हो तो यहाँ पे हल्की सी चीज़ें रिवाइज कर लो, ठीक है. There's nothing to be discussed before discuss. There's no need of discussing this differential equation before doing this discussion. So y is equal to c1 plus c2t into e raised to the power mt. Okay. Now suppose let us take various cases. M is greater than 0. Let's take sub cases like m is greater than 0, m is equal to 0, m is greater than 0, m is equal to 0, m is less than 0. If m is greater than 0, then the value of yt at t tending to infinity. Check simply. M is greater than 0 as t tends to infinity. This value makes it infinity. And this time also becomes infinity. So ultimately, your answer is infinite. And infinite means unbounded. Unbounded means unstable. Infinite means unbounded. Unbounded means unstable. ठीक है? So by this discussion also you can make some more conclusions. I'll come to that conclusions. Don't worry. If m is equal to 0, then what is yt? Yt, if m is 0, this thing becomes equal to 1. And the value of yt at t tends to infinity, this linear term is going to make it infinite. So that is infinite. Okay. Infinite means unbounded. Unbounded means unstable. Okay. Correct. Unbounded means unstable. Fine. Okay. So if m is less than 0 in that case, if m is less than 0, then yt at t tends to infinity. Now, it's not a very complex limit problem. If t tends to infinity, this term approaches 0. However, this term increases in magnitude. But you know, this is a linear term and this is an exponential term. So the contribution of exponential is dominated, and therefore, ultimately, this thing approaches 0. And this can also be solved mathematically by using various rules of solving the limits. You can check if you want. So 0 is finite, and finite means bounded, and bounded means stable. Again, some conclusions we can make from here. What are the conclusions? If the roots or if the poles of the transfer function are real and repeated, in that case, they should be negative, then only the system will be stable. Let's take the third case. The third case is case 3. What is the third case? The roots are imaginary conjugate pair. Roots are imaginary conjugate pairs. Conjugate pairs. Okay. Imaginary conjugate pair. You know that the conjugate pair exists as alpha plus minus iota beta. We have done this discussion in the dynamics of second order system also. Do you remember what was the solution here? The solution was yt is equal to e raised to the power alpha t c1 cos beta t plus c2 sin beta t. You also know that this can always be written as e raised to the power alpha t then multiplied by some r sin beta t plus phi. ऐसा लिखा जा सकता है. You know that this kind of expression can be written like this by using some trigonometric identities. Now, depending upon, tell me about this thing. Whatever be the value of time, this thing results value always between +1 and -1 because of sine function, and then multiplied by r. So it is very obvious that the term present inside the bracket is always between, this will give you between, value between -r to +r. It will never become infinite or finite. So whatever problem will arise, that will be due to this e raised to the power alpha t, or I should say alpha. So see, in these cases, we made various cases with m1, m2 and m. But here, आप किसके केस बनाओगे? बीटा के केस बनाओगे या फिर अल्फा के केस बनाओगे? See, whatever be the value of beta, it is going to be between -r to +r. So you will make cases for alpha. So what are the cases? Alpha greater than 0, alpha equal to 0, or alpha, let's take less than 0 first, alpha less than 0. Do you remember something which I told you from this, what is the role of this e raised to power alpha t in the in the underdamped system? Please recall. Okay. If alpha is more than 0, then as the value of yt as t tends to infinity will be, this is -r to +r, this is always finite, but if alpha is positive and as t tends to infinity, this term tends to infinity, so this is infinite. Infinite means unbounded, unbounded means unstable. So infinite means मैं unbounded नहीं लिख रहा, अभी unstable लिख रहा हूँ. ठीक है? Okay. Second case, if it is negative, this is always finite. As time tends to infinity, yt, the value t tends to infinity, this outer term is going to make it 0. And 0 is finite. 0 is finite and this is called stable. Fine? Okay, this is a very special case. If alpha is 0, I told you, what is the purpose of this e raised to power alpha t, the damping, right? If alpha is 0, in that case, the yt value is r sine theta or beta t plus phi. Now, what is this? This is simple sinusoidal curve. There is no damping, there is no decrease in oscillation. What is the meaning of this simple sinusoidal curve? That if alpha is 0, there is क्या कहा था एक मैंने sustained oscillations. Response yt oscillates continuously. Oscillates continuously. Yt oscillates continuously. So आप इसको bounded बोलोगे या unbounded बोलोगे? Of course it is bounded. There is no doubt. Because it is continuous oscillations are always in a maximum and minimum limit. So it should always be called as bounded. तो बोलेंगे तो bounded, there is no doubt. But I should call it stable or unstable. That is the problem. I should not call it stable. I should not call it unstable. So here, please note that I will use a word which is called critically stable. Which is called critically stable. Now this is my differential equation discussion. Note down. अच्छे से इसको clearly note कर लेना, table बना लेना. But why I discuss these things? So that now I can conclude everything and I can give you some points which you can use to check the stability of the system. But please note that here I have used the poles, the roots of the auxiliary equation m1, m2, alpha, beta, all those things. So in case of when I'll make the conclusions, I will use the poles of the transfer function instead of the word roots of the auxiliary equation. They are same thing. Okay? I hope you have noted down. So let us now conclude the things. तो एक बार सारा erase करते हैं. Fine. And now we will be talking about whether the system is when the system is stable or unstable. What are the various cases? Okay. And how we can conclude this discussion. I mean, if you ask me that, sir, मुझे तो बस 2-3 पॉइंट बता दो जिसका यूज करके मैं ये बता दूं कि सिस्टम स्टेबल है कि नहीं है. बट वो पॉइंट्स मैं डायरेक्टली लिखवा सकता था, बट वो यहां से आता है. There is a reason, there is a logical explanation that from where the statement comes that the pole should be negative. Here it is the mathematical explanation. You can see that in most of the cases we found that if the pole is negative, the response was bounded and hence it is stable, because initially I defined the stability of a system as that case where the response is bounded on giving bounded input is called stable system. So what do we have? We have conclusions. Very, very important to check the stability of a system. What are the conclusions? First, conclusion 1. For a system to be stable, all of its poles, its pole means poles of the closed loop transfer function, all of its poles must be negative. This was the conclusion, because you saw that whenever a root is positive, the response was unstable. So even if a single pole is positive, the response is unstable. Even if a single pole, कोई भी एक पोल पॉजिटिव नहीं होना चाहिए. ये मैं कैसे लिख रहा हूं, अपने आप लिख रहा हूं क्या? नहीं, we just found this, we just concluded. You can see everywhere, right? Even if a single pole is positive, in that case the system is unstable. तो ये मैंने आपको एक conclusion दे दिया. What is the conclusion? That whenever you write a transfer function and you find the poles, all the poles must be negative. What else we can conclude? Okay, if one pole is 0 and rest of the poles are negative, if one pole is 0 and rest of the poles are negative, this was also one case, na? One pole was 0 and one pole was negative. So even if rest of the poles are negative, then the system is stable. Yeah, is stable. Okay. But secondly, in case of multiple poles at origin, one pole is 0 means pole at origin. In case of multiple pole at origin, you saw na, when there were two poles were equal to 0. 0 means 0 value, not the numerator. When two roots were equal to 0, in that case, but in case of multiple poles at origin, whenever you have multiple pole at origin, the system was unstable. The system is unstable. मैं यहाँ पे एक और point add करा दूँ. When in case of multiple poles at origin, the system is unstable irrespective of the nature of other poles. Means you should not say कि sir देखो rest of the poles are negative, कोई बात नहीं, system stable होगा, नहीं. Even if you have two poles at origin and all the other poles are negative, doesn't matter, the system will be unstable irrespective of the nature of other poles. Irrespective of the nature of other poles. ठीक है? But in case of multiple poles at origin, the system is unstable irrespective of the nature of other poles. That was the third point. Fourth point. What is fourth point? ठीक है, ये चीजें हमने देखी थी, है ना? One more point. Suppose if the poles are imaginary conjugate pairs, if the poles are imaginary conjugate pairs, imaginary conjugate pairs, pair I should write, not pairs. If the poles are imaginary conjugate pairs, then the real part must be negative. The real part must be negative, then only the system will be stable. We saw na, when alpha was less than 0, then the system was coming to be, the response was coming to be finite and bounded. Real part must be negative. If the poles are, imagine the real part must be negative for the system to be stable. For the system to be stable. Okay. These are 4 conclusions which we can make from the previous discussions. So first of all, note them. है ना? So what is the main point here? The main point that we have discussed, for a system to be stable, all of its poles must be negative or should have negative real part. ठीक है, एक ही पॉइंट में सारी बातें बता दी, बट यस दिस ऑल्सो मल्टीपल पोल के बारे में आपको एक स्पेशल केस है जो आपको पता होना चाहिए, दैट इवन इफ ऑल द पोल्स आर नेगेटिव, one pole is zero, the system is stable. But even if all the poles are negative, two poles are zero, multiple poles at origin, three poles are zero, the system will be unstable. Right? These are the conclusions. ठीक है, तो हम लोग क्या करते हैं, whenever you read books, you will find this written directly, but from where it came. It is not like, it is not experimentally found. No, it is theoretically found only. ऐसा नहीं कि experimentally find किया गया. What was the definition of stability? I gave you initially the definition of stability. I used the same definition of stability in those mathematical calculations, and now I'm giving you this, the conclusions. So the conclusions were derived theoretically. There is no practical, there is no experimental explanation for this. Theoretical explanation. What was the theoretical explanation? I gave you in mathematics. Right? Now let's say that, okay, I told you that, okay, fine. I told you that what should be the location of poles for the system to be stable. But let us see this graphically now. कि कैसा रिस्पॉन्स आएगा एग्जैक्टली. सो नोट कर लिया होगा, बिकॉज आई विल नीड द एंटायर बोर्ड फॉर दिस डिस्कशन. ओके, सो अ ग्राफिकल रिप्रेजेंटेशन ऑफ द रिस्पॉन्स फॉर different location of the poles. Let's see. Okay, put the heading that graphical representation of the response, graphical representation of the response, graphical representation of the response for different location of the poles, for different locations of the poles. ठीक है, graphical representation of the response for the different location of the poles. Okay, suppose I'm giving step input. Suppose I'm giving step, whatever I'm drawing here, it is with respect. If I'm not mentioned, if nothing is mentioned, I'm doing it for step input. Don't worry. Now suppose, let me use various colors here. Okay, suppose the poles are, see, this is called complex plane. Complex plane समझते हो ना, imaginary axis, real axis. We have done this in mathematics also. This is called complex plane. In the complex plane, we denote this y-axis and we call it imaginary axis. And we take, complex plane is also called argand plane. Okay, and this axis as a real axis. Suppose your roots are real and negative. Okay, roots are real and negative. Roots means your poles. Suppose you have poles present here. Roots are real and negative. How you are going to make this equation in that case? So how you're going to make the response in that case? The response is, of course, we have discussed that if the pole is real and negative, the response should be stable. What is the meaning of stable? Bounded, right? Now see how the response will look like. The response, I have to make the response stable. So how a stable response looks like? Know that a stable response must be bounded, right? Fine. A stable response must be bounded. So how to make a bounded response? Tell me, what is the meaning of a negative pole? The transfer function must be something like this. See, numerator, let's not talk about the numerator. The transfer function must be something like this. Numerator by s plus a. Correct? Then only you'll be getting negative pole if a is positive. So what is the Laplace inverse of this? Yt is equal to e raised to the power minus at. Yt is equal to e raised to the power minus at. Fine. If this is your transfer function, in that case yt will be equal to e raised to the power minus at. Fine. How to draw e raised to the power minus at? How to show this response? E raised to the power minus at, exponentially decreasing response. Fine. Suppose you have this as okay. So it means why I took this example, because it will be exponential. Exponential means monotonically changing. Fine. So what kind of response it will be? It will be something like this. आपको monotonous response बनाना और stable बनाना. Suppose this is the ultimate value and it will be like this. This is called monotonous, right, and stable. right? Monotonous and stable. This kind of response will be there. It will be monotonous and stable. Fine, monotonous, stable. Suppose we have another case that now the pole is, now I'll not write every time imaginary axis and real axis. Suppose this is the scenario, fine. But now the pole is present. Pole is suppose like this. You know that if the points are present here, they are conjugate pairs, right? So this is alpha plus iota beta and this is alpha minus iota beta. You can see yourself that alpha is negative. Alpha is negative, it means the response must be stable. Now how the stable response looks like? Now what is the difference between this table and this table? The difference is this response will be oscillatory. You know that if the roots are imaginary conjugate pairs, in that case the response comes out to be oscillatory. Oscillatory response aata na? But what is the meaning of oscillatory stable? Stable oscillatory means this is the thing, stable oscillatory response. YT, so this kind of response is oscillatory but stable. So देखो stable दो तरह से हो सकता है, oscillatory में stable और monotonically changing में stable. Now what are the other cases? You can have this case as well, that your response is your roots, or sorry, your poles of the transfer function are purely imaginary. You understand what is purely imaginary? Means alpha is equal to 0. Purely imaginary means iota beta and minus iota beta. If this is the scenario, the response will be something like this. Suppose, okay, the response will oscillate about a particular value. What kind of response it is? It is continuously or sustained oscillation. This kind of response is called oscillatory, neither stable nor unstable, right? This response is oscillatory. देखो ये कैसे decide होगा कि response oscillatory है? If the roots are conjugate pair, then definitely response will be oscillatory. But in conjugate pair, if the alpha is negative, the response will be stable. If alpha is 0, the response will be critically stable. Oscillatory, critically stable. Okay, why? Because alpha is 0, critically stable. There is no e raised to the power alpha t to damp this. I told you that this equation is equal to e raised to power alpha t, where alpha is negative, critically stable. Okay, fine. What is the other possibility? The other possibility is still the roots can be conjugate pairs, but the alpha value can be positive. In that case, where the poles will lie? देखो मैं कभी-कभी root बोल रहा हूँ, कभी-कभी pole बोल रहा हूँ. Deliberately, because you must know that roots and poles, they are same thing. But roots is for the auxiliary equation of the differential equation and poles are for the transfer function. So poles word we generally use in S domain and roots word we generally use in time domain. Fine. See, roots are imaginary. If roots are imaginary, of course the response will be oscillatory. Imaginary होने से unstable होगा ऐसा नहीं है. If roots are imaginary, it is causing oscillations. But if alpha is positive, then the response should be unstable. Now, how you can draw instability in oscillatory response? Like this. There is no damping. In fact, damping is there. You can say that negative damping is there. This is called oscillatory and unstable. तो unstable oscillatory में भी हो सकता. Oscillations का मतलब unstable नहीं होता. Oscillations have nothing to do. Oscillatory, I should write oscillatory. Oscillations have nothing to do with stability. Right? We don't have problem with oscillations unless it is this kind of oscillation. Okay, oscillatory and unstable. Now you may ask, sir, what is the last case? Think about it. The last case will be real and positive pole. Real and positive pole. Suppose the pole is present here. The pole is positive. A real and a positive pole. Fine. If this is the scenario, because the pole is real, the response should be monotonous, exponential. But because it is positive, it must be unstable. How you make unstable response in monotonous way? This is the thing. Monotonically increasing and unstable. Non-oscillatory, है ना? Monotonically increasing means non-oscillatory. You can also use the word non-oscillatory. monotonically increasing and unstable. ठीक है? This is the some more understanding of stability. तो देखो एक चीज ध्यान रखना, देखो the response will be oscillatory or non-oscillatory is decided by the fact whether the roots are real or imaginary. Fine. The response will be stable or unstable is decided by the fact whether the real part is negative or positive. So you can have oscillatory and still stable, and you can have non-oscillatory and still unstable. तो stability का oscillation से कोई लेना देना नहीं है. Stability has nothing to do with oscillations. Oscillations are completely different thing. Stability is completely different thing. So you can see yourself that what are the various possible cases, right? So in this lecture, I have discussed everything about, you must know now that which response should be called as stable response. Fine. So I also gave you conclusions. So now I guess if I give you a transfer function, or if I give you a closed loop, right? If I give you closed loop, you can always do the block diagram reduction or use the shortcut for feedback control loop. You can always write the closed loop transfer function. When you write the closed loop transfer function, see what is the denominator, find the poles, check the nature of the poles, comment about the stability. Are you getting this? You have the 4 conclusions that I gave you. But for using those 4 conclusions, you must know the roots of the denominator. Now here comes the problem. Sometimes the denominator is a quadratic or cubic equations, which is easy to solve, and you can find the roots and then you can comment about the stability. But sometimes the denominator can be 6th power of s, or even if it is 4th power of s, finding the exact roots of the solution takes time. It means, abhi tak, whatever method I have discussed here, if you want to comment about the stability of the system, you must know the poles of the transfer function. Without finding the poles, we can't comment about the stability so far. That is why we have a test. That is not the definition of stability. We have a test. That test is called Routh stability test or Routh-Hurwitz criteria. So it is known by both the names, Routh-Hurwitz criteria or Routh stability criteria. Now the Routh stability criteria, what is the purpose? No need to go through, sir, from where it came, how it was derived. Totally out of your context, out of your scope. Okay, out of our context, out of your scope. Okay, Routh test must, you know that how to use that Routh test to comment about the stabilities. Why Routh test is there? So that you can comment about the stability of a control system.